Electrical components and properties. Now that we have discussed the basic principles that govern an electrical circuit, let's discuss the components that affect the way that an electrical circuit works. Batteries. Batteries are essentially electrical generation devices that adhere to the DC voltage generation principle discussed in this chapter. The three most common types of batteries are dry cell, which is the kind you buy to put in your television remote or children's toys, wet cell, which is for cars and boats, and storage batteries. Also called deep cycle batteries and used in remote, backup, emergency, and industrial electrical systems. Figure 6.11 illustrates the schematic symbols for a single cell and a multi-cell battery. The symbol consists of a long bar and a shorter bar. Although schematics might not always indicate the positive and negative terminals, the long bar always represents the positive terminal, and the shorter bar the negative terminal. Multi-cell battery. Single-cell battery. Figure 6.11 schematic symbols for single-cell and multi-cell batteries. When you want more energy than a single battery or power source can provide, you have several options that will provide more voltage, more current, or modest improvements on both. Although this discussion pertains only to batteries, it applies to any form of multiple power sources. Series connection. When you connect batteries in series, you can achieve an overall voltage that is equal to the sum of the individual voltages of the cells, but you will get only as much current as any one cell in the battery chain can supply. For example, if you connect 6 12-volt batteries with an individual amperage of 15 amps in series, you will achieve 72 volts, but will maintain a total current of only 15 amps. Exam alert. Connecting batteries in series equals the sum of the voltages, but maintains single-cell current. To connect power sources in series, you connect the positive terminal of the power distribution panel to the positive terminal of the first battery. Then you connect the negative terminal of the first battery to the positive terminal of the second battery, the negative terminal of the second battery to the positive terminal of the third battery, and so on. Until you connect the negative terminal of the last battery to the negative terminal of distribution panel. Figure 6.12 illustrates a set of 6 batteries connected in series. Parallel connection. When you connect batteries in parallel, you can achieve a total output current that is equal to the sum of the individual amperages of the cells, but you will get only as much voltage as any one cell in the battery chain can supply. For example, if you connect in parallel the same 6 12-volt, 15-amp batteries discussed previously, you will achieve 90 amps, but will maintain a total voltage of only 12 volts. Exam alert. Connecting batteries in parallel equals the sum of the amps, but maintains single-cell voltage. To connect power sources in parallel, you connect the positive terminal of the power distribution panel to the positive terminal of the first battery. Then you connect the positive terminals of each battery in the chain together. Next, you connect the negative terminal of the first battery to the negative terminal of the distribution panel, and connect the negative terminals of all the batteries in the chain together. Figure 6.13 illustrates a set of 6 batteries connected in parallel. 12V15A plus series parallel connection. In some circumstances, you might find that you need to increase both voltage and current. In those cases, you should connect your batteries, or power sources, in a series parallel configuration. Let's take the same 12-volt, 15-amp batteries that you were using earlier as an example. If you have a system that requires 36 volts at 30 amps, you can connect them in series parallel, as figure 6.14 illustrates. By connecting 3 of the batteries in series, You increase the total voltage of those batteries to 36 volts, and you do the same with the other 3 batteries, for another 36 volts. Then connect the 2 sets of 3 batteries in parallel, to increase the current to 30 amps. Photovoltaic cells. Photovoltaic cells, or solar cells, are semiconductor devices that convert sun energy into electrical energy. Solar cells are made of semiconductor materials. A thin semiconductor wafer is specially treated to form an electric field, positive on one side and negative on the other. When light energy strikes the solar cell, electrical current is produced. Solar cells are often used to charge batteries, such as for solar landscaping lights, but the resulting electricity can also be used immediately. Several solar cells can be connected to each other and mounted in a support structure or frame to create a solar panel that can be on a standalone support structure or on the roof of a building. The solar panels are configured to supply electricity at a moderated voltage. Most commonly, this is 12 volts. However, the current produced directly depends on how much light strikes the module. Electrical wiring. Electric circuits and equipment connect to a power source via electrical wires, or cable. Different electrical applications require different sizes and types of wire, and the amount of current that will be traveling through the cable is the determining factor in choosing wire size. The higher current a circuit needs, the larger the diameter of the wire must be. Current flow through a wire increases the temperature of the wire. If too small of a wire is used, it will heat up and cause a reduction in voltage and possibly a fire. If the wire is large and the current is small, the heat coefficient is small. The thicker the wire is, the more current it can carry without overheating. Gauge numbers define wire sizes and get bigger as the wire diameter gets smaller. The amount of current that a given size of copper wire can carry safely, or its amperage capacity, is its ampacity. Several types of cable are specified for electrical wiring. Plastic sheathed, indoor type non-metallic sheathed, NM, for indoor household wiring and other dry, protected locations. You might hear it called Romex, which is a brand name for this type of cable. Armored cable NM for indoor and other dry locations. Armor keeps cable from chafing during and after installation. NMC, non-metallic, corrosion-resistant, for moist, damp, and corrosive locations, including the hollow in concrete block, and for both below and above ground. Cable insulation colors. Most 110 wiring that you will see is either 12 or 14 gauge NM cable. Almost all new homes are wired exclusively using NM cable. This cable has 3 wires inside a sheath, and each wire is designated for a specific purpose. Table 6.2 correlates each wire color to its intended function. Splicing cable. If you need to splice, or permanently join, wires together, you have 3 choices. Solder the joints. Soldering takes a bit more time, effort, and tools. But it connects the wires electrically as well as mechanically. A properly made solder joint is as strong as the original wire, and offers no additional resistance to the flow of current. Use screw-on wire nut connectors. A screw-on connector makes a solderless connection that can be permanent in most applications. To use wire nuts. Put the 2 ends of clean wire together and push them into the connector. Because the wire nuts are threaded inside, you can then screw the connector down tightly, like a bottle cap, onto the wire. Use wire crimps. Wire crimps are short copper cylinders into which you insert the ends of the stripped, clean cable wire. You then use wire crimps to squeeze down the crimp firmly around the wire.